Howdy folks, in this pre-work we're going to continue our discussion of exponential and logarithmic functions. In this one pre-work I can't cover everything. So we had a basic overview of inverse functions in a previous pre-work you can access here. We had an introduction to just the logarithmic operation, which you can access here. And then we've already done a pre-work that introduced the exponential and logarithmic functions. And so this would probably be the most helpful one. If you find anything I say in this video confusing or seems like I'm assuming some knowledge that you don't have, fall back on this pre-work right here. I think that should help cover things. Okay, let's take a look here. So based on the previous work we've done, if I suppose that a is a real number greater than 1, I can ask you to quickly sketch the graph of a to the x, and this was what was done in the previous pre-work. So this would be the graph of a to the x. There's the graph of a to the x. Here we're assuming that a is greater than 1 here when we sketch this. And we saw that, for the exponential functions, we have a couple of easy to plot points on here. For example, if we were to plug 0 into this exponential function, even though we don't know what a explicitly is, anything to the 0th power, any positive base to the 0th power, we'd find to be 1. And similarly, this is the other nice point on here. If here's when x is 1, a to the first power is just a, so there's the order pair 1a. So you've got these couple of nice points on here on this exponential function that are easy to graph. The other thing we should always sketch with our exponential function is prior to any transformations or any compositions, we have a horizontal asymptote at y equals 0, and so we should label that. So at this point we can go ahead and give the domain of f. So let's go ahead and, I should say that this was f of x here, so I'm going to change that. F of x is equal to a to the x. So the domain of the function f, we see is just minus infinity to infinity. That is, we know how to take a number a, any number bigger than 1, and raise it to any exponent, whether that be a integer, it could be a negative number, it could be a 0, it could be an irrational number, although that's a little bit harder to talk about. But we can take any number and raise it to the appropriate power or exponentiate it. So our domain is from minus infinity to infinity. And we can see that from the graph here. If you were to collapse this graph onto the x-axis, you would see what its domain is. Similarly, we can give the range of the exponential function, and the range is anything from 0 to infinity. It's worth noting that, for example, if I gave you something like f of x is equal to, let's do g of x is equal to 2 to the x, that there is no number I could plug in for x that would output a 0. For example, if we were to plug in g of 1, that would spit out 2 to the first power, which is just 2. G of 0 spits out 2 to the 0th power, which is 1. G of, say, minus 1 would spit out 2 to the negative 1 power, which is 1 over 2 to the first, or 1/2. And so you see there's no, it's a quick explanation, there's no input value that I can put into an exponential function to have it output 0, and so we have as a range 0 to infinity. Similarly, what we said in previous pre-work, you could look at collapsing this graph onto the y-axis here, and you would see the range. The fancy phrase is projecting it onto the y-axis, and we'd see that the range is from 0 to infinity. Okay. So then we learned also in our previous pre-work how to sketch the graph of this inverse function to this. And the inverse function to this, even though I didn't say it explicitly in this problem, is the log base a of x. So this is f inverse of x is equal to log base a of x. I'm going to rewrite that. And so that's one way to think about it. I mean, if you're struggling with logarithms, it's just a name that we give to the inverse of the exponential function. And there's other ways to think about them. One thing to point out is that the original function, a to the x, passes through the order pair 0, 1. And so as we developed last time, we saw that this passes through the order pair 1, 0. Likewise, the exponential function, when I input a number 1 into it, it just spits out the base. And so if we take log base a of a, so there's the input a, that's going to spit out the order pair a, comma, 1. That's that domain range flip-flop between a function and its inverse. And also with that domain range flip-flop, we would say that the domain of f inverse would be the range of f. So the domain of this inverse function is from 0 to infinity. Likewise, the range of this logarithmic function here, we know from our construction of inverses, is just going to be the domain of f. So this is from minus infinity to infinity. Similarly, we can kind of infer this from the way I wrote the domain here, from the graph. But there is no number that I could plug into the, or I'm not allowed to plug the number 0 into the logarithmic function, any log, regardless of the base, prior to transformations. But if I were to plug in numbers that were positive and close to 1, I would get, or close to 0, I would get large negative numbers. And we can see here that just like the graph of a to the x has a horizontal asymptote at y equals 0, the graph of log base a of x has a vertical asymptote at x equals 0. And we should always label those for our logarithms. Now, in a moment here, I'm going to let you all tackle these problems here, but soon I'll have you practice graphing both the exponential functions and the logarithmic functions, including those transformations, similar to what I did at the end of the last pre-work, so you get some more practice with that then. Okay, folks, well, that wraps up this first video of the pre-work. In the next video, we'll be looking at the domain and range restrictions for the exponential, or for specifically the logarithmic functions, and we'll put that in the context of the other functions we've worked with. So I'll see you in the next video.